This is the module of biochemistry. Actually, they will have two components. There's a component of cell and molecular biology, and this is structural biochemistry and metabolism. For today, we are going to start the cell chemistry. Me who is presenting Evelyn Kanarama. I have a Master of Science in Medical Biochemistry, and I'm doing a PhD in medical sciences. So, concerning assistant lecturer, data structural biochemistry and metabolism. Component, I think you have seen the teaching plan. This course, I mean the biochemistry, the whole molecules and the reactions occurring in the cell and behavior health and diseases. And this component, chemistry, will be based on two books, not only books, but those mainly are available online. If you encounter the problem of downloading access, you can ask your librarian to help you. But those books are very important. Our main in this of objectives. In this presentation of today, the first is to define and describe the importance of biochemistry in your field, physical mathematics. Is why you need to know chemistry. And just the purpose of the goal, the main goal to what you have seen in secondary school. We see about atoms, structure, type bonding, molecules, isomers, properties of water, pH and buffers, and then I don't talk about chemical presence. Just this presentation have the main purpose of him to see school, and it provides the basis to attend the following talks. Now biochemistry. Biochemistry. In biochemistry, you see you have bio means life, and chemistry, you know about chemistry. Now together biochemistry is the chemistry of life. It is a science which deals with the chemical processes that governs life. Chemically explain the characteristics of living things, such as the chemistry behind the reproduction process, behind growth, the chemistry behind development and death, the chemistry behind the environment, and so on. Processes behind it. So, about those processes govern life. Now, why should you learn about biochemistry? as health professionals, mainly physicians and pharmacists, why do you know about as I was to know the process of life, as we need to know about the process of health and disease. This biochemistry provides basic knowledge that serves as a guide in the understanding of health and disease. It helps the treatment and the management of diseases. It helps also in designing drugs for treatment of those diseases. So to diagnose the disease, you need to know the test. So that is a process and know the drug that will treat the such kind of disease. So important for you. I think you are interested in about this. Now let's start going what we have seen in secondary schools. The concept of atoms, element, molecules. Matters are composed of extremely small particles called atoms. Contain only one type of atoms and cannot be broken down into anything simpler through reactions. So elements combine to form a compound or a molecule. And here we have an example. Just all atoms being on are made of atoms. And the atoms of same properties but if the sodium lose one negative, I mean one electron means one lose one negative, so it remains with extra positive. Sorry. It remains with extra positive. So many protons compared to electron. The same on chlorine. Before chlorine had the equal number of electrons and protons. For now, there is an additional electron that make it to be negatively charged. I mean, the extra negative compared to positive. So those atoms now become charged. Because opposite charges attract, the sodium and the chloride ion remain associated in an ionic compound. This NaCl, which is electrically neutral. Therefore, ionic compounds are crystals, and most of them dissociate in water. Now, let's see. Let's talk about this covalent bond, where atoms share their electron. Sorry. Here we have two atoms. Here we have two hydrogen atoms sharing their electron to make hydrogen molecule. The same as fluorine, two fluorine atoms share their electron to make fluorine molecule. When bonding atoms have the same or closer electronegativity, the covalent bond formed is called an nonpolar covalent bond. Now here we are going to talk about or to see when we say a bond is polar or a covalent bond is nonpolar. Also, we base on the electronegativity. When the atoms have the same or closer electronegativity, the resultant bond is nonpolar covalent bond. For example, here, the bond between hydrogen and carbon will be nonpolar covalent bond because their electronegativity is very close. So the difference is low. If they are different and have high difference in electronegativity, the formed bond is covalent bond, as there will be a creation of partial charges on bonding atoms. This is the case of hydrogen and oxygen. When you look on the electronegativity on the periodic table, you will see that the oxygen have high electronegativity compared to hydrogen. When even there is a sharing of electron between those two atoms, the oxygen have this high capacity or this high ability to attract more electrons from hydrogen, and this will create partial positive and negative charge. Hano bimeze nk'uko abantu babiri barushana intege bahuriye ku kintu. Even the weak remain together, sharing with the strong, but the high amount, if I can say, will be on the stronger. In this case, electronegativity has the ability to attract electron. Oxygen will attract more compared to hydrogen. Those shared electrons will be 80% belong to oxygen, and a small percentage belong to hydrogen, and this will create those partial charges. Now, in the water molecule, hydrogen is a partial. Sorry? Any concern? Hello?
Yes, we are still together.
Are we together?
Yes, we are still together.
Okay. For any concern, don't hesitate to interrupt me. Right? Now, because carbon atoms possess 4 valence electrons, it can form 4 covalent bonds, and the molecules containing carbon can form straight chains, branches, or even links. So you can see here carbon skeleton, because it can form 4 covalent bonds at the same time. We can have this open this chain, we can have branches, even links. Bonds between molecules, different type of bond between molecules. So before we were talking about the bond between atoms, covalent, ionic, these are bonds between atoms to form molecule. And remember, if we say water, for example, molecule of water, we don't have only one. Let's take a cup of water. There are millions and millions of molecules of water in the cup. Now we are going to see those interactions between molecules in the same compound, if I can say. You see, molecules are not isolated. When they are in the medium, then there is the interaction between those molecules. So neighboring molecules may interact either by attraction or repulsion, depending on their chemical properties. These interactions are weak compared to ionic or covalent bonds formed between atoms. Here, you need to differentiate bond between atoms and interaction between molecules. Important bonds found in biological molecules here we have hydrogen bonds, van der Waals forces, hydrophobic interactions, and electrostatic interactions. Generally, for important interactions between molecules, here our interest is in biological molecules. We have those at least 4: hydrogen bonds, van der Waals forces, hydrophobic interactions, and electrostatic interactions. This is very important. Always try to remember this, because in structural biochemistry, most of our talk will be based on those 4 kinds of interaction between molecules. Now let's see hydrogen bonds. Yes, okay. I was saying that we need to differentiate a bond between atoms and a bond between molecules. Remember, 2 or more atoms put together to form a molecule. But a molecule is not isolated. Generally, I gave an example of a cup of water, where we have billions of molecules in a cup of water. And those molecules, of course, they are interacting to be maintained in that container. There is interactions between those molecules of water, for example. Not only molecules of water, but all molecules interact. And those interactions possible between molecules, and as our interest here is those biomolecules or biological molecules, there are 4 important bonds or interactions between molecules. There is hydrogen bonds, van der Waals forces, hydrophobic interactions, and electrostatic interactions. And I say those kind of interactions are very important in this structural biochemistry, because not only in structural biochemistry, but generally biochemistry, because those bonds will help us to understand the structure of biomolecules. For example, a sophisticated structure of a protein, how plasma membrane lipid bilayer arrange. It is all about those kind of interactions. Okay? Now, let's see hydrogen bonds. Hydrogen bonds are attraction forces between polar molecules with high difference in electronegativity. Hydrogen bonds can be formed between hydrogen and oxygen, nitrogen and chlorine. Now, look at here. There is hydrogen bond that can be formed between fluorine and hydrogen, oxygen and hydrogen, then nitrogen and oxygen. And this hydrogen bond is based on is mostly available in polar molecules. Sorry. Now, in polar molecules, we have partial charges. For example, in a molecule of water, remember this is partially negative and this is partially positive. So this attraction will form as long as we have this negative charge and partial positive charge in the medium, this interaction will occur. And this interaction, remember, is based on the difference in electronegativity. And here you see hydrogen and nitrogen, the possibility of the hydrogen bond between nitrogen and oxygen is because of this lone pair of electrons on this nitrogen. Hydrogen will be attracted to this free pair of electrons on the nitrogen. Now, van der Waals forces, interaction between non-polar molecules which temporarily become polar because of unequal distribution of electrons around their atoms. They can be attraction or repulsion. Yes. It is not shared. Oh, sorry. Let me check. Can you see it now? Okay, good. I was saying van der Waals forces. In the previous slide, we have seen the interaction between polar molecules where partial charges attract. But now here we have non-polar molecules that need to interact. Now, interaction between non-polar molecules is based on the unequal distribution of electrons. Remember, we have seen that in the structure of atom, we have seen that electrons keep moving around the nucleus. Now, it is now understandable that when 2 or 3 atoms are put together and their electrons keep moving around, there will be a temporal or a temporary dipole that will be created. For example, this is, sorry. Now this is an atom with the nucleus in the center, and sorry, in this case we are dealing with molecule. Sorry, this is a molecule with atoms making it, and each atom have the electron now that are turning around. Now, sometimes electron may be on one side of the molecule. If electron is on the one side, it means on the other side will remain, let's say, a positive, if I can say. There is an imbalance. Electron should be, to be neutral, electron should be distributed in the way every side we have, let's say, equal amount of electrons, if I can say. But if they are moving, they are sometimes the period where they are on one side, on the other side there is an imbalance. There's a few electrons. I'm saying that if they are moving around, they can be on one side, leaving the other side a few electrons. If the same happen on the other molecule in the medium, also electron on one side. Sometimes, if those molecules are together and electrons are distributed such a way this positive and negative are together, there will be attraction. If electrons are distributed in the way the same charge are in contact, there will be diffusion. Just here, the idea behind this Van der Waals forces is this an equal distribution of electrons around atoms making a molecule. Now, if electrons are distributed in this side, on this side, on the other molecule, at this side, there will be attraction. If electrons are distributed so that positive or negative are on this side, there will be diffusion. Just here is about an equal distribution of electrons around atoms making a molecule. Is it clear? Okay. Now, hydrophobic interactions. Hydrophobic substances do not mix with water. Remember, in hydrophobic, excuse me, here, it is not visible. What happened? Can you see it now? Ndeke gushyira muri slide show. Size is okay. Can you read? Yeah, I'm putting in a presentation mode like this. Are you seeing it? Okay. Hydrophobic interactions. I'll say that hydrophobic means those molecules that cannot mix with water. Hydro is with water, phobic hate or fearing. Now in water, hydrophobic molecules tend to clump up together rather than distributing itself in a water medium. Sorry. Yeah, because those hydrophobic substances are not polar, so they cannot form a bond between water. Maybe for a substance to be soluble in the other, there should be a kind of reaction. That means they form bond with that solvent. In the case of water, any substance that cannot form bond with water cannot be soluble in water. Now, hydrophobes cannot form a bond with water, so in water they clump up, they try to hide, they put together. And now here we have an example of when you mix fat and water. As fat cannot react with water, the fat will be put together aside, they not mix with water. For example, when you put water on the surface of leaves, iyo inyamaswa ibintu by'igiti ntabwo ashobora kwinjiramo because the waxes on the leaves, those lipids on the leaves cannot allow water to enter because there is no bonding between water and the waxes on the surface of the leaves. Now can you see what's wrong? Okay. Now, electrostatic interactions. Those interactions happen when there is intramolecular ionic bonds between charged amino acid residues in a protein, for example. The same in this magnesium and ATP. Just here, electrostatic interactions is in this structure where we have disturbing. Okay. Electrostatic interactions, it means the formation of charges, the presence of charges, and this allow attraction between those charges. These are electrostatic interactions where we have some charges interacting. This is the case of polypeptide, where the same molecule, amine group and the carboxyl group interact. This is another example of ATP complex with the magnesium. Magnesium is attracted on negative charge of oxygen in phosphate group. Now, about molecule representations. In chemistry or biochemistry, molecules are represented differently. This is the same molecule represented in different ways. This is a computer-generated space filling model, and this is a computer-generated stick representation. This is extended line drawing showing all atoms and the bonds, where all atoms and the bonds are shown. Yes. Oh my goodness. Sorry, here. From here. On electrostatic interactions. Are you seeing the molecule representations? Can you see it now? Ntabwo nzi ikibazo kiri. Ndimo ndashyira muri slide show. Rimwe mukayibona ubundi ntimubibone. Ubwo murabibona se? Okay, I don't know. Twajya tubyihangana n'ibitagaragara rimwe mumbwira nongere minimize nongere nsubiza minimize nabisubizaho bikongera bikaza. I don't know what's wrong with my laptop, but it's okay. Just to show the representation of molecules. I was saying this is the same molecule represented differently. You can find the molecule represented as this. This the first in A is the feeding model. B is a stick model. C is extended line representation where all bonds are drawn. And in D is a standard line drawing, the most used in teaching here when we are trying to write on blackboard, on paper. We use this kind of standard line drawing. But this is the same molecule represented differently, just to show molecule representations. Because in books, in some books, or when you are trying to do your searching, when you are reading, you may find all those different representations. So nothing complicated here. You are concerned with at least this structure and this, to know this. No one will ask you to draw this. This is computer generated. What you can do with our hands is only those two. Now, can you see the slide about isomerism? Okay. Don't worry. Now you can. Now, isomers are molecules with the same composition, but with different chemical and physical properties. Isomers are molecules with the same composition, I mean chemical composition, but with different chemical and physical properties. You may have functional isomers where in abbreviated you have carbon, hydrogen, and oxygen, and in that brief formula you have, one can make an aldehyde, the other can make alcohol, the other can make a ketone from that formula. So aldehyde and the ketones have somehow different properties, like I say. Just here, isomers, the same chemical composition, but different chemical and physical properties. Generally, there are three categories of isomers. We have structural isomers, where we have the same composition but different connectivity. We have conformational isomers, which is a result of bond rotation. We also have stereoisomers, where we have geometric isomers and optical isomers. They have the same atomic connectivity, but different spatial arrangement of the constituent atoms. Let's see one by one. Here we have a structural isomers. Now you can see this, right? We have the same atomic composition but different arrangement. Here we have this structure. You see how they are the same, but this methyl group is here in a, if say second position. Here it is on the third position, and here is on the fourth position. Still the same atomic constituent, but different connectivity. The position of this one. These are structural isomers. The same as here, we have 4 carbon. Here they are arranged or extended, they are linearly, but here they form kind of a branch. These are structural isomers. The structure only. Now we have conformational isomers, molecular forms that arise as a result of rotation around the free rotatable bond are known as conformers. Now you can see the slide. Okay. For each and every slide, I will do the same like this. You can see it now. The single bond have this flexibility of rotation. The single bond can rotate. In this rotation, it can form different forms of molecules. But the stable one, the most stable is the one which will exist. Others cannot be observed, but at least some can be observed, but the more stable is the one which will predominate. A molecule can have different conformation in solution, but the most favored predominate. Example here we have succinic acid that has 2 conformations. Now, any single bond here can rotate, but the rotation between this carbon and this one is the one which will impact this molecule, as with this rotation you can at least have 2 forms of succinic acid. Now, in this, there is succinic acid conformation 1, this one above. And when this bond rotates, we can have this part coming down and have the conformation 2. Both forms are possible, although conformation 1 is more favorable due to the greater distance between the carboxyl groups and therefore occur more frequently. You see, this is our COOH, the carboxylic group here. We have another carboxylic group here below. And in both 2 conformers, the most stable is this one, where those 2 groups are sufficiently separated to avoid the hindrance. This one will not, or will can be formed, is possible, but not favorable compared to this one because of this hindrance. If I can say en français, it is called a complément stérile. It means there is a hindrance. I mean, it will not stable because the interaction of this between this one will cause this molecule to not be stable. But as this is away from this one, at least this is more stable compared to the below here. Is it clear? Okay. Now, are you seeing geometric isomers slide? Okay. About geometric isomers, we have two kinds of geometric isomers. We have those cis-trans isomers and stereoisomers. Now, in cis-trans isomers, those isomers are possible where we have double bond. This double bond are not cannot rotate. They are not freely rotatable. Therefore, other bonds around this double bond can rotate, but this bond is not flexible to rotate. So this is a single bond, and it's a single bond. Those bonds can rotate so that this can come here, the other can remain here or come here. In the other way, they can rotate. So rotation about this double bond will make either cis configuration or trans configuration. Cis-trans isomers have different chemical and physical properties. They can only be interconverted by chemical reactions. So to change a cis configuration into trans configuration, there should be a chemical reaction, differently from conformation, where conformation is just a rotation of a bond in the same molecule, only rotation. But in this configuration of those cis-trans molecules, there should be chemical reaction to change from cis to trans. Okay? Yes. Yes, there will be intervention of external factors like irradiation, for example, that will change from cis to trans. Otherwise, without those external factors, there's no way to change trans to the cis to trans or trans to cis. There should be external factors. Let's see on the following slide where we have an example. Remember those retinol or retinal, I don't know, those visual pigment. Now you can see on the slide. Yes. To change this, to change this 11 cis retinal into all trans retinal, we require the intervention of light. You see, here we have cis retinal, and in the presence of light, light will target this bond and make the cis is changed into trans in the process of vision. In physiology, I'm sure you will see this in physiology. the process of vision. This is what I was saying, that in conformation, we have seen it before, just rotation around single bond. But in this cis and trans isomers, or cis or trans configuration, this configuration is different from conformation. Now, here, there is an intervention of the external factor that causes a reaction, a chemical change. There is a change, a reaction occur here due to this light, and this cis is transformed into trans. Is it clear now? Are we together? Now it is clear, I think. Okay. Mm-hmm. Mm-hmm. The question? Yes, there is a change, but it is not spontaneous. There should be an influence of external factor, let's say that. Now, optical isomers. If we say optic in physics is it implies the use of some lenses or mirror, whatever. I don't know. I'm not good in physics, but if we say optical, it is a kind of physics there. But in our case here, we are mentioning these optical isomers in terms of the deviation of light, the polarized light, and those optical isomers, when in solution, have the ability to rotate the plane polarized light. This plane polarized light, as I was saying, there is much of physics, but remember, when you have a source of light, the side is divergent, if I can say, up, down, where, and here, if they say polarized, there is an instrument called the polarizer that will make those dispersed rays make it as a focused one. Polarized, it is straight, it is channeled, and those polarized light, when pass through a solution of having those isomers, on the detector, the sign, if there are some substances that turn that light in the left, turning the kind of murushinge, I don't know, even you are in physics, you can see it on the detector, like this murushinge can detect on the voltage or whatever. That's on the detector, the light will turn in left or right. Those rotating the light to the right, I mean clockwise, are said to be dextro rotatory, and they have a positive sign. They are indicated with a positive sign. And when in solution, we have a substance, and the light passes through that solution, and the light turn to the left, I mean anti-clockwise, that substance is called revoltatory, and it is indicated with the negative sign. Optical isomers exactly are identical in physical and chemical properties, but differ in the action of the plane polarized light. Just here, those optical isomers are the same in chemical properties and physical properties, but the difference is the way they deviate or they turn this polarized light. Now, in short, we have a solution with those chemical substances, and the light pass through the solution. And when you look on the detector, you see the light is the turn to left or to right. In that case, you will know this substances is have optical activity at the first, and this optical activity of turning this light, it turns the light either on the left, on the side, or the right. Now, this notation of plus or minus in biological molecules or in molecules, that's indication of how those substances can turn the light, and to say that they have optical properties. And here, when you have a mixture where you have those dextrorotatory and levorotatory substances at the same time, the mixture is called racemic mixture, and that mixture will be optically inactive. They will not deviate this polarized light. And now, let's see enantiomers. Those enantiomers are also optical, sorry, geometrical isomers. They have the same atomic connections, but a different three-dimensional arrangement of atoms. And they are non-superimposable mirror images of each other. This is an exercise you are familiar with, I'm sure, when you were in secondary school. Your teacher talked about those mirror images. When you put a mirror, your hand in front of the mirror. If it is the right hand, the image in the mirror will behave as if it is your left hand. When we say they are non-superimposable, it is because you cannot put your hands together and see the thumb are together unless you blink the other side. That is really not an image of your hand. To be the image, it should come as your hand is. Now, in that case of those molecules, it is the same. They have the same connectivity and the same atoms, but when they are arranged, it is different. For example, here, when you have a mirror between those atoms, you see on this picture we are trying to show enantiomers. These are the pair of glyceraldehyde enantiomers, non-superimposable mirror images, and the other importance here is this carbon here. where we said that enantiomers should always have one or more chiral carbon. A chiral carbon is this one with 4 different groups. We have hydrogen bonded to it. We have hydroxide group. We have this group and this group. All are different. So this carbon is a chiral carbon or make a chiral center. Just to show how the one is the image of the other. Now it is more sorry. It is more visible on this sorry, on the when we will be talking about the carbohydrate monosaccharide, we see how those images are formed, but here also you can see it. If this were the image of the one here, this should be here. Inkaho nawe ndeba imbere nawe ukaba tutonze umurongo ndi imbere undi inyuma kugira ngo tube turi superimposable, but in this case kugira ngo iyi ibe ari image y'iyi nuko nayo yagombaga kuba ihagaze nk'uko ihagaze, iyi ikaza aha ibi bikaza hano hirya, ariko azi byaje ku ruhande gutya, so byaba bigiye guhoberana kugira ngo bibe bigerekeranye, niba bisobanuye neza. Ariko the enantiomers is about the mirror images, nta kindi. When the one is a mirror image of the other, that cannot be superimposable, they are enantiomers. If you find it is an image which is superimposable, they are called their stereoisomers. Okay. A question? No question. Now functional groups. A functional group is an atom or group of atoms arranged in a particular way that is primarily, excuse me. Oh, sorry, I forgot. Now you can see the slide. Now I was saying that a functional group is can be atom, one or more, or a group of atom that is responsible for chemical and physical properties of the molecule. Now, all compounds having a particular functional group are members of the same family. Let's see on the following slide where we have different types of functional groups found in living things. Just here to show we have different kind of functional groups. I don't know if it is possible to zoom and still continue to see the slide. I don't know. Okay. Now just to show different types of functional groups. We have this we have methyl group, ethyl, ester, sulfide, thioester, and so on. This you can read on your own, just to know when we say functional group, what do we mean? These are functional group. When we say behavior of carboxylic acid, when we say physical properties or chemical properties of alcohols, what do we mean? On the next slide, we have this picture of acetyl coenzyme A, just to have this information that in one biological molecule we can have many functional groups. On this example we have here, you see, we have thioester group, amido group, phosphoanhydride group, imidazole group, amino group, phosphoryl group. All this structure make this acetyl coenzyme A. Yes. Mm-hmm. In this, for example, this is acetyl coenzyme A, where we have many functions. The one which will dominate, as if I can say, for this group, mostly this thioester group, but depending on the situation, any functional group can dominate depending on the situation. But mostly in this acetyl coenzyme A, the most active we used to observe is this thioester function in biological systems. But in the other system or in other condition, you may find any other group dominate, but mostly in biological systems, this one is the most one that function to transfer acetyl groups. No, in this case, there is no need to search know if this amino will dominate, this one will dominate. Generally, a molecule behave according to the medium. For example, if you have an enzyme, let's say an enzyme, in basic condition, it will behave differently in acidic condition. Or sometimes depends on the medium a molecule is. Yeah. Now, I think the most important part of the presentation, you have seen it. The remaining part is about, it's a kind of like information. Here, element involved in biological processes, saying that from 92 elements occurring in nature, about 25, here we include those trace elements, whatever, mainly 6, we have carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Some books say 4. They say this carbon, hydrogen, oxygen, and nitrogen. Others may say it depends, but generally, those for the phosphorus is added because it is very abundant in nucleic acid. This is mostly added because the part of protein, so it's okay. But bear in your mind that all 92 elements that are present in nature are not all found in biological systems. And in those elements, we have some are organic, others are inorganic. We say that a compound is organic when it contains carbon, with the exception of carbon monoxide and carbon dioxide, carbonate, those are considered as inorganic. So other carbon-containing compounds are organic compounds. Inorganic are not containing carbon. They include water, acid, alkalis, and mineral salts. Of course, in inorganic, we include carbon dioxide, carbon monoxide, carbonate, and so on. Inorganic compound of the cell. Now we are talking about the cell. In the cell, we have water. The majority of cellular content is water, and 70% of living organism, let's say our body, 70% is of our total weight is made of water. And the 95% of total cellular water is used by the matrix as the solvent for various inorganic substances and organic compounds, and is known as free water. The remaining 5% of total cellular water is linked in protein by hydrogen bond, or water forces is the bound water. So water which is found in the cell, they are what we call free water. That is a solvent, soluble part of water of the cell, that's free water. And there's another part of water bound in molecules in hydrogen bond with the proteins, with the carbohydrate and so on. These are bound water. I think in your assignment, you have to talk about the properties of water. So much of the remaining slide here is in your assignment. Even you have other questions in the previous slides, but about properties of water, it's up to you to read, but water is a universal solvent. This is common. Water is a polar. And water, you talk about cohesive properties of water, adhesive properties of water. You will talk about evaporation heat, melting point of water. All those properties, you need to read it and try to work on it in your assignments. Another property associated with water is this ionization of water, where we define the pH scale. And the pH scale is defined based on the ionization of water, and how we come up with the the formula of this notation or this information saying that water is neutral, pure water at 25 degrees centigrade, where we say that pH is neutral. So I want you to read the rest of this presentation about the properties of water. It is associated with this pH scale. Another thing you need to know about this pH scale, you will also read about the buffers. Also, a question about buffers, if I remember, in your assignment. About acid and bases, this is a recall I want you to read on your own. Long and weak, whatever. I want you to read about all this. And after reading this presentation, of course, you try to remember what you have seen in secondary school. You read the provided reading material, use slides. You ask me where possible. I said you can ask me in any way. You can use WhatsApp, you can use email, you can use SMS, you can even write on the platform. I see you are not visiting the platform. And remember, the platform is our main place that we can meet. I've uploaded all materials, materials for tomorrow are there. And I put an announcement there. I think nobody have read it. Am I wrong? Who read the announcement on the Moodle?
Twayibonye.
Mwayibonye? Yego. Iminota isigaye reka tuvuge ikinyarwanda mu minota isigaye kuko presentation y'uyu munsi irasa n'irangiye. Kuko iyi minota isigaye ndagira ngo tuvugane uko tugiye kwiga. Niyo mwabonye announcement, ariko mfite impungenge ko abanyeshuri bose batarabasha kuba enrolled on Moodle. What is wrong? Umuntu wese uri mu iri shuri ari enrolled kuri Moodle? Pepe, tell me. Abanyeshuri babashije kwinrolinga kuri Moodle? Yewe. Mu gitondo narebye nsanga hariho abanyeshuri 155. Kuri lisite wampaye hariho abanyeshuri 200. Niba ari n'abane, nidushyiraho 31 biga ko nagombye kubona lisite iriho abanyeshuri 235. Nyuma yo kwiga nimugoroba ko mufite quiz, kuko nta bundi buryo ngo mbasha nanjye kuinshuringa attendance. Nishuringa attendance, yes, murasinya kuri liste mufite, ariko kandi njye nyirebera no mu makwizi mwakoze.